Hi, in this video, I'm going to go through the AS-level Chemistry paper, AS-level Chemistry paper, AQA paper. This is paper 2. It's the 2021 paper. I'll just do the first half in this video and complete it in the next. Okay, the first question is about the Maxwell-Boltzmann curve then. Okay, so label the y-axis on the figure. Well, we've got energy on the x-axis, and this is the number of molecules on this axis, or the number of particles. Now, state why the curve starts at the origin. They don't ask this question very often, once every few years. And look, here it starts at the origin because 0 molecules have 0 energy. All the molecules have got some energy. Right. Then it says, state what X indicates on the figure for 1 mark. What is X? X, well, I usually say it is the most probable energy of the particle. It's not really the mean because the curve is asymmetric, but it is the mode. It's the most probable energy of the particles. Right. Half of the gas molecules in the sample are removed. The remaining gas molecules are kept at the same temperature. Okay. Draw the new molecular distribution. Well, if you don't change the temperature, you're not really going to change the distribution. You're just going to have half. So every single point on that curve will be half as high. So that one will be about there. That one will be about there, 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 so on. So you'd be something like that. But noticeably, the X, the most probable energy, doesn't actually change at all. It's only if you change the temperature, you'll change the shape of the curve. Okay, so next question then we have about the reaction of bromine with alkenes. Name and outline the mechanism. Well, of course, this mechanism is electrophilic addition. Okay, and now we've got to outline the mechanism. Right, why does this happen? It's because you get an induced dipole. So bromine Br2 obviously doesn't have a dipole, permanent dipole, because both bromines got the same electronegativity, but that will become delta positive because it's close to the high electron density in the double bond there. Okay, so it will induce a dipole, and that delta positive bromine is the electrophile. It's attracted to the high electron density. Right, a pair of pi electrons are going to come out, so draw a curly arrow like that onto the bromine. Then the bond between the two bromine breaks. Right, that is going to give us an intermediate. We're going to have a bromine stuck to one of the carbons. The double bond has gone, the pi bond's gone, that's why it's addition, and there will be a positive charge on that carbon there. That's a carbocation. Okay, right, and then finally the Br minus, draw a lone pair on the Br minus ion. That is then going to, those electrons go into the positive carbon, and we're going to make the product 1,2-dibromocyclohexane. Right, that is the mechanism. 5 marks. Right, explain. I sort of explained this already. Explain why there's an attraction between the CC double bond and the bromine molecule. Right, because the CC bond, I'd say that there's 3 important points there. It's high electron density. And that induces a dipole in the Br2 molecule. Okay, and so that delta positive end of the bromine molecule is attracted to the CC double bond. Draw the skeletal formula of the haloalkane formed when 1,3-butadiene reacts with an excess of bromine. Okay, so we just draw 1,3-butadiene out. You've got double bonds there and there. These are hydrogens. I won't bother drawing all the hydrogens on. Right, what's going to happen is you're going to get an excess of bromine. So bromine is going to add across both double bonds. So first of all, you're going to get that there. And then that one as well. Right, it's asking us for a skeletal formulae. So here is that's the skeleton, okay, and then we've got a bromine on the end there. Got a bromine on that one there, bromine there, and a bromine on that one. So it's a bit confusing, I think, there, but you can see that they're the carbon atoms there. Yeah, they're the 4 carbon atoms. That's the skeletal formulae. When I say it's a bit confusing, it looks like, I always think that is a carbon and that's a carbon as well. Of course, they're not. Yeah, there's just 4 carbons there. Okay, propanone can be reacting propan-2-ol with an excess of acidified potassium dichromate. Okay, so that of course is an oxidation reaction. So we just draw where we got propan-2-ol is a secondary alcohol, and if you oxidize it, you're going to form propanone, ketone. Okay, shows the apparatus. So they're refluxing it with acidified potassium dichromate. Okay, and the apparatus, and there's going to be mistakes in this apparatus. Oh, they're not refluxing; they're just distilling it off. Sorry, there's going to be mistakes. 3 problems with the apparatus. Right, the most obvious one is there should be number 1. There should be that should be sealed. There should be a bung in there, and you probably usually have a thermometer in there as well to monitor what temperature the distillate's coming off. So that's one mistake. The second mistake is the water in and the water out. The water should go into the bottom one and out of the top one, so the whole jacket fills up with water. And then the third one is like a little bit less obvious, and I had to have a little peek at the mark scheme, I confess, to see what they're really looking for, and it's just anti-bumping granules. Okay, that's what they wanted there. Okay, so for each problem, identify the problem. Might have identified it. Describe the issue to cause. Right. No bung. What would be the issue to cause? All the propanone would just come out the top, and you wouldn't get it. How can you resolve it? Put a bung in the top and with a thermometer so you can monitor the temperature. Is a good idea. Right, the red one, the water in, the water out. The condenser might not get cold enough if you had the water coming in the top. It would just trickle through without filling up the jacket, and you might lose more of the propanone than you should do. Some of it might not condense. And finally, the anti-bumping granules here. If you didn't have them, it might boil too violently, and some of the liquid could splash down the condenser there, and you'd end up getting dichromate in your propanone, which obviously you don't want. Okay, right, now we've got a percentage yield thing coming up, I think. Right. Okay, so student reacts 2 centimeters of propan-1-ol, okay, with an excess of potassium dichromate, and it tells us how much propanone we get. Right, we need to know the mass of propan-2-ol first of all, and we need to work that out from the density of the propan-2, which they give here. So mass is equal to density times volume. The density is 0.786, and the volume is 2 centimeters cubed. That is going to give us 1.572 grams of propan-2-ol. Okay, so now we need to work out the number of moles of propan-2-ol, and look, we know that 1 mole of propan-2-ol gives us 1 mole of propanone. That's why I put the equation there. So let's do the moles of propan-2-ol. Right, that's going to be mass over mR. The mass we've worked out is 1.572. And the mR of propanone is 60. So that gives us the number of moles is 0.0262. Right, now the next thing we need to say is that 1 mole of propanone, propan-2-ol gives us 1 mole of propanone. So the moles of propanone is the same. So if 100% yield, what should be the mass of the propanone? It's moles times mR. That is equal to, so we've got 0.0262 moles, and the mR of propanone is 58. That gives us a mass of 1.5, sorry. That gives a mass of 1.5196 grams. Right, we know we didn't get that much. We got this much propanone, so we have to work out the percentage yield. So percentage yield is equal to actual mass over the expected multiplied by 100. So the actual mass was 0.954. Divided by the expected, this one here, 1.5196, multiplied by 100. And that gives us 62.779. Right, now it says to significant figures, appropriate, I'll give it to appropriate number of significant figures. Well, the least accurate bit of data they've given us here is only to 2 significant figures. That's the volume of the propanone. So that is all we should give it to. So we should only give it to 2. So that's going to be, round that up, that gives us 63%. You shouldn't say 62.8. That would be 3 significant figures. Right. Right. Molecules of propan-2-ol and propanone each contain 3 carbon atoms. Complete table 1 to suggest the shape and the bond angle around the central carbon atom in a molecule of each compound. Okay, let's look at the central carbon atom. So I've drawn these here. Look at the central carbon atom in propan-2-ol. You can see it's going to be tetrahedral. There are 4 bonds formed there, 4 bond pairs, and there's no lone pairs. Carbon never has lone pairs, and it's 4 bond pairs. Right, so that's going to mean it's going to be tetrahedral, and that means that bond angle is, so this the shape there is tetrahedral. And that bond angle is 109.5. That's a tetrahedral bond angle. Right, now with propanone, right, what have we got here? We have got 3, with a double bond, remember, when you're working out the shape of molecules, a double bond, just treat it as a single. And you can see there you've got 3, effectively got 3 bond pairs, and we've got no lone pairs. Carbon never has lone pairs, hardly ever. Okay, so that means it's going to be trigonal planar. The shape, and the bond angle, of course, for that is 120 degrees. Okay, explain why propanone has a lower boiling point than propan-2-ol. Right, this is all, of course, down to the intermolecular forces, and you can see that here, this hydrogen on propan-2-ol, that can form, that's going to be very delta positive because it's attached to electronegative oxygen. So that can actually form hydrogen bonds to the OH group on another propan-2-ol molecule. Okay, so you can get hydrogen bonds in that, which you need to say are the strongest intermolecular forces. Whereas if you look at propanone, you can see that it's only permanent dipole-dipole interactions. That's all you're going to get there. Oxygen is electronegative, so that's going to be delta negative, and that's going to be delta positive on the carbon. But none of these hydrogens can form hydrogen bonds because they're not attached to oxygen, nitrogen, or fluorine. They're attached to carbon. They're not delta positive enough to form hydrogen bonds. Okay, so you get hydrogen bonding in propan-2-ol. You don't get it in you only get dipole-dipole interactions in propanone. Hydrogen bonds require more energy to break. The boiling point is higher. Right, question 4. Okay, CFCs were used as refrigerants and in aerosols in 1974. So this is about ozone depletion. Ozone molecules are depleted from the upper atmosphere. Okay, a few years later, other scientists discovered that the concentration of ozone in the atmosphere was decreasing, and they were banned by 1987. Okay, so the molecule CFC11 is there. Use then IUPAC names to name that. Okay. Right. Right. So we have got 3 fluorines. So it's trichloro, fluoro. It's got 1 fluorine, methane. We put the chlorines first because alphabetical order. Fluoro, C before F. So trichlorofluoromethane is the answer there. Okay, 4.2, a molecule of CFC11 breaks down the upper atmosphere to form a chlorine-free radical. Give the equation for the reaction. Okay, so let's draw that out. Okay, so you get UV light, it will break the bond, and you're going to end up with that free radical and the chlorine-free radical. Okay, so the pair of electrons in that bond, one goes to the chlorine, one goes to the carbon. It's broken by the UV light. Right. A typical refrigerator contains 0.5 kilograms of CFC11, and it gives its MR. 1 molecule of CFC causes the destruction of 100,000 molecules of ozone. Use these data to estimate the number of molecules of ozone that can be destroyed by 0.5 kilograms of CFC. Okay, so, and they give us the Avogadro constant. So if we want to work out number of molecules, the first thing we need to do is work out number of moles and then multiply by the Avogadro constant. So let's do moles of CFC11. That's going to be mass over the MR. We've got to be careful there because they've given us the mass in kilograms. So we need to convert that to grams. So that's 500 grams divided by the MR, 137.5. That gives us 3.636 moles. So now we need to work out the number of molecules we've got there of that. So multiply it by the Avogadro constant. Molecules of ozone. It's going to be moles times by the Avogadro, L. So that's 3.636 times 6.022 times 10 to the 23. That comes out to be 2.19. Sorry, 2.18 times 10 to the 2.189 times 10 to the 24 molecules. Well, not this is not molecules of ozone, this is molecules of CFC11, sorry. Right. So we've got that many molecules of CFC11, and it tells us here that each one of those can destroy 100,000 molecules. So let's do molecules of ozone destroyed then. Is going to be that number, 2.189 times 10 to the 24, multiplied by 100,000, which is 1 times 10 to the 5. So that comes to 2.189 times 10 to the 29 molecules of ozone destroyed. Okay, state the benefit to life on Earth of ozone in the upper atmosphere. Well, of course, it filters out UV light, and UV causes mutations, damages DNA. Right. So just one reason why the use of CFEs was not restricted into several years after Rowland and Mullany produced it. That's one of those funny questions, right? You can suppose you can say anything for that, really. So I'd probably say uh, it took a while for international agreements to be drawn up. Okay. And I think it does say that, gives that one in the mark scheme. Right. That's question 4.6. Right. CFC 11 is a greenhouse gas that can contribute to global warming. State and explain how CFC 11 can contribute to global warming. Okay. Right. Well, you need to say, first of all, of course, the reason why it causes global warming because it can absorb infrared radiation. But then it's two marks. You have to say why can it absorb infrared radiation? Now it's because it contains polar bonds. The mark scheme, I think, is actually not quite right. It says because it contains polar molecules. And that's true of CFC 11. It is polar. Yeah, it's like that. But if you think of carbon dioxide, which does absorb infrared radiation, it's not a polar molecule because it's symmetrical, but it does have polar bonds. Yeah. So I think it's more correct to say because it contains polar bonds rather than that it's got polar molecules. But there you go. Right, I need to change to the next whiteboard now. That's the end of question 4. Okay, question 5. Right, this question is about polypropylene. The 3 steps to manufacture polypropylene from crude oil. So crude oil, you get naphtha, and then you get propylene. Step 3, turn it to polypropylene. Naphtha is a mixture of alkanes with 6 to 12 carbon atoms per molecule, it tells us. For each step, name the process and state briefly the purpose of the process that leads to the formation of polypropylene. So we've got 6 marks, and 1 for naming each one for a bit of explanation. Okay, so let's say step 1. What is the first step? Step 1. Right, for each step, yeah, because it's step 1 to 3. Right, step 1, of course, how do you get naphtha from crude oil? Fractional distillation. What's the purpose of that? Is to separate molecules, into fractions. And fractions are mixtures of molecules with similar boiling points and similar length, yeah. Boiling points. Right, step 2. What we're doing here, we're turning naphtha, which is 6 to 12 carbons, into propene, which is only 3 carbons, so making them shorter. So what we're doing there is we are cracking. Step 2 is cracking. What does cracking do? It makes it breaks molecules, larger molecules into smaller ones. And it also introduces a double bond into some of the product, yeah, which of course we need for the next step. To get propene, you can't polymerize propane, it needs to have a double bond in it. So that's important. The final step, step 3, is polymerization. Okay, that's step 3, polymerization. done it here. Bit of room. What's the purpose of doing that? Well, it's to join lots of similar small molecules or identical small molecules into a large molecule. Okay. Question. Right. Right. I think I missed a couple of questions off there. Right. So it does say question 5.2. It says, why is polypropylene not biodegradable? The reason it's not biodegradable is because it's all you've got in the backbone is that you've got carbon-carbon bonds. They're not polar, and that means they're difficult to break. It's kind of probably not really appropriate question for AS, because really I think they usually ask that question in the A level when you've done polyesters. Okay, polyesters have that linkage in them like that, and they are biodegradable because you've got a polar bond there. Okay, but in this one, carbon-carbon bonds are not polar, so they're difficult to break. And then the next question, 5.3, scientists, they say, are developing biodegradable polymers. What are the benefits of biodegradable polymers? That's pretty obvious, really. It's only a 1-mark question. Is so that they don't persist in the environment, cause problems like most plastics do. Okay, question 6. I've got an ideal gas calculation here. Right. In the first experiment, liquid X is injected into a sealed flask under vacuum. The liquid vaporizes and assumes a certain volume in a gas syringe. Calculate the relative molecular mass of Y. So they give us the mass, they give us the temperature, they give the volume of the flask. Okay, so what we have got to do, we've got to get the ideal gas equation. So we have PV is equal to nRT, and we have moles, N is equal to, do it in a different color. The other equation we have moles, N is equal to mass over the mR. So we're going to substitute N with the green, and we'll end up with one equation here, which is going to be PV is equal to mass RT over the mR. We need to rearrange that to get the mR. So mR is going to be equal to mass RT over PV. Right, we've got all the numbers here, and so we just got to put those in. But before we do that, we'll be really careful with units, as always with the ideal gas equation. Right, so the first problem with the units is we've got this in mass in milligrams, so you need to convert that into grams, so that's 0.717 grams. The temperature is in Kelvin, that's okay, not degrees C. The volume is in centimeters cubed, and we need to convert that into meters cubed. Now, there are 1 million centimeters cubed in 1 meter cubed. So 482 centimeters cubed is equal to 482 divided by 1 million meters cubed, which is equal to 4.82 times 10 to the minus 4. And then finally, the pressure, we need to convert that into pascals, not kilopascals, so that's 51,000 pascals. So let's put those numbers in there. So we get MR is equal to the mass 0.717 multiplied by the ideal gas constant 8.31 multiplied by the temperature 297 divided by the pressure, 51,000, multiplied by the volume, 4.82 times 10 to the minus 4. And that gives us a value of 71.887 exactly. So let's round that up to 71.9. That's the three significant figures, right? Because all the data here, that's all given to three sig figs. So that's what I should give my answer to. Right. In the second experiment about the gas, another flask is used for a combustion reaction. Okay. Right. So they've removed all the air from the flask. They put in 0.01 moles of trimethyl pentane, and they add this much oxygen. And they spark the mixture to ensure complete combustion. So because they say complete combustion, that the oxygen must be in excess there. Okay. Well, we could show that, but it obviously is in excess. And the cooler mixture is the original temperature, so that means that the water is going to condense out. Calculate the amount in moles of gas in the flask after the reaction. Okay, how are we going to do that then? Right. So we've got 0.001 moles of that, of the trimethyl pentane. Now that is going to react with, and we've got, well, let's put that, we've got 0.02 moles of oxygen at the start. How much oxygen is going to be used up? Right. So moles oxygen used. Look, 1 mole of that needs 12.5 moles of oxygen. So it's going to be how many moles of that? We've got 0.001 multiplied by 12.5, which gives us 0.0125 moles of oxygen used. So how much oxygen have we got left over? Well, it's the original amount, 0.02 minus 0.0125. And that is equal to 7.5 times 10 to the minus 3 moles of oxygen. Okay, so we've got that much oxygen left over. We need to work out the total moles of the gas. Okay, okay, so we've got that much oxygen. Now, we've got all of that is all reactive. That's all gone. So the only other gas we've got there is carbon dioxide. Right. How many moles of carbon dioxide are we going to have? Well, 1 mole of C8H18, that gives us 8 moles of carbon dioxide. So that means that how much do we have of that? We had 0.001 is going to give 8 times 0.001, which is equal to 0.008 moles. Okay, and what we need to do now is add the total moles of gas. So this is the moles of oxygen left over is that, and the moles of CO2. So the moles of gas at the end is equal to 7.5 times 10 to the minus 3 moles of oxygen plus 0.008 moles of carbon dioxide. That is equal to 0.0155 moles of gas at the end. Okay, on to question 7. Right. Propanone is a natural chemical found in garlic. It is also used in the production of plasticizers. Okay. Propanone can be prepared by reacting 3-chloropropane with dilute sodium hydroxide. Name the mechanism of this reaction. So it's confusing when you're dealing with names like that. So I've drawn them out. So we've got the 3-chloropropane there in red, 3-chloropropane in red, and we have got the product there in blue, and you can see all that we have done there is that we have swapped a chlorine for an OH. So the way you do that would be nucleophilic substitution, isn't it? You'd use sodium hydroxide in an aqueous solution. So nucleophilic substitution is the answer for 1 mark. Nucleophilic substitution is the answer. Right. Now, we have now got to Prop-2-ene-1-ol can be formed from this is actually a diol, isn't it? This is propane 1,3-diol in the presence of an acid catalyst. Name and outline the mechanism for this reaction. Okay, so what I have done there is I've drawn here. I've drawn the diol, and you can see here we are going to remove our hydrogen from that middle carbon and the OH from the neighboring carbon, and that is going to introduce a double bond here between those 2 carbon atoms. Right, now the name of the mechanism is elimination, and we've got to show a mechanism for it. Right, so the first step in the mechanism, we need an H plus catalyst. Okay, so the lone pair on the OH is going to form a bond to the H plus. That's going to give us this intermediate. Right, we've now got a positive charge on that oxygen, which makes it a lot easier to break the bond between that and the carbon. That's why you need the acid catalyst. Okay, now that leaves, that bond breaks, and so that goes onto there, and you're going to release water, and of course that's going to leave a positive charge on that end carbon now after that. So we've now got H2O come off, and we've got positive charge there. And that bit is untouched. And what happens now, you're going to lose one of those H's. So that is going to go there. So the electrons in the bond between the carbon and the hydrogen is going to form the pi bond part of the double bond to give us the product, and you're going to release the H plus. So you can see the overall role of the H plus is a catalyst because it doesn't actually get used up. So there we got our double bond as our product. Okay, that's that mechanism. (7.3). Okay, Prop-2-ene-1-ol forms an addition polymer. Draw the repeating unit of this. Okay, so what I like to do is when you're doing this is think of it as just being like ethene. So you know, if that was just an H there, that would be ethene, wouldn't it? Okay, but it's not an H, it's a CH2OH. So what's going to happen is that you're going to break that bond and that bond, and you're going to form a new bond between those 2. So you can see the repeating unit is going to look like this. We need to draw those bonds there. I always put brackets around it. I think they don't actually insist on the brackets, but that's the repeating unit. Okay, now we've got infrared spectrum question coming up here. Okay, this shows the infrared spectrum of a functional group isomer of Prop-2-ene-1-ol. Okay, so it is C3H6O, but it contains it's a functional group isomer, so presumably it doesn't contain a CC bond, right? And so if it's got that ratio of carbons to hydrogens, you can see that it probably has got to contain another double bond, a C double bond O. Okay, that's probably what it's got there. Okay, right. So let's look at the spectrum. Okay, so this bit, of course, is the fingerprint region. We're not interested in that. This bit here is definitely corresponds to the C double bond O. Not only has it got the right wave number, but it's the kind of right shape as well. They're usually quite deep and fairly broad, those peaks. Okay. So, and here this is CH. These are the CHs, and when it's quite broad like that, it's quite often indicative that it's an aldehyde. Okay, which it wouldn't really, it doesn't say that in the mark scheme, but it is when it's broad. Very often it's an aldehyde. So the isomer reacts with acidified potassium dichromate. So if you think C3H6 with a double bond though, it could either be the aldehyde. Would that react with acidified dichromate? Yeah, it would, because you can oxidize a dichromate. You can oxidize an aldehyde to a carboxylic acid. So that's what we've got. And just to rule out the it couldn't also C3H6O, that is propanone. And propanone, of course, though, you can't oxidize any further. It is a ketone, so it wouldn't react with potassium dichromate. So the answer is the aldehyde there. Okay, I'm going to leave that. That's about halfway through the paper, so I'm going to leave it there and carry on in the next video.